Hi, everybody. Thanks for coming to my talk. This is presenting a bunch of work that I've been doing with my colleagues, Anders Freund, Bilal, and Melanie, and a lot of input from other people as well. Okay, so the overview of the talk, I'm just going to talk, first of all, a bit of a super quick review of some operating system facilities that are relevant to this stuff. Because I find a lot of people aren't really aware of the changes that have happened over the past, I'm going to say 40 years in I/O I/O interfaces. I'm going to have a quick historical review of that and then move on to talking about read streams, write streams, and where we hope to go with this. So here's three different sort of concepts that go together and work quite well together in databases. We've got buffered I/O versus direct I/O. We've got vectored I/O, which is also known as scatter-gather I/O. And we've got synchronous I/O versus asynchronous I/O. And I'm going to look at what those things mean and concretely how they look in an operating system. So if you go back to the 1960s, there was this system called Multics, which was the predecessor of Unix. And if you look at its name, it was the multiplexing computing system or something like that. So multiplexing was in the name, and it had the ability to read and write data from a file, but you could turn it from synchronous mode into asynchronous mode with this work sync function. And then you could call read, start reading some data into a buffer, and then a bit later when you're ready to consume that data, you would call I/O wait, and that would give you your CPU time to go and do something else in the meantime while the I/O is happening. And the team that did Unix, Dennis Ritchie and Ken Thompson and so on, Bell Labs pulled out of Multics famously, and they started producing Unix, which it started with a joke named the uniplexing control system or computing system, whatever it was. So it's actually in the name that they got rid of the concept of asynchronous I/O. And they were well, first of all, I think they were very constrained because they had a PDP-7 with a tiny amount of memory, and they needed to fit a kernel into so many kilobytes or whatever. But also they were quite opinionated about, they wrote papers about how most people don't actually need the complexity of multiplexing. And in fact, if you think about the programming languages back in that time, it would have been pretty hard to write programs effectively that could drive a lot of multiplexed I/O. So through the 80s and 90s, the systems that derived from that early Unix pretty much stuck with the basic synchronous read and write functions. You call read. When it returns control, the read is finished. Maybe it came from the cache, maybe it came from disk and you had to wait, but you can't even tell. And throughout the 80s and 90s, a few small additions were made to those functions. The P variants, so that you can specify the position in the file you want to read from, and the vectored variant, where you can take some data and read it from a chunk of data and then scatter it into several different places in memory at the same time. But that's pretty small changes. Also, there was the concept of direct I/O came up in several, I think it was IRIX that did it first, and all the other Unixes adopted that. That was never standardized, but it was widely used by proprietary database systems in the 90s. So in 1993, I should say this is parallel universe over here of all these contemporary operating systems. They all had asynchronous I/O. IBM mainframes had, I think they call it channel I/O. The DEC operating systems like VMS had QIO, I think they called it. And obviously Windows NT derives, a whole lot of concepts came from VMS into Windows NT, and it has the same kind of asynchronous I/O built into the operating system at a very basic level. So in 1993, POSIX came out with asynchronous I/O functions, and they never really took off. A lot of Unixes, including Linux, but also several of the proprietary. A couple of the proprietary Unixes did a really good job of implementing it, and they were mainly used by proprietary databases again. So ways to start a read and then wait for it later if you have to. But Linux never implemented that properly, and it's really not that widely known. They're very obscure functions that very few people understand. And I think there are a few design issues with the way it was done. Much later, there was the libaio system, which has got a bunch of kernel support and some ways to do asynchronous I/O in Linux. Again, only ever used by databases as far as I know. And much more recently, IOU Ring offers from 2019, so pretty recent, offers a really a complete rethink of the way that type of programming interface should work. And it seems to be having a lot more success. A lot of people are really interested in that programming model. And I think we're going to be hearing a lot more about IOU-ring. Andres Freund here was doing a lot of research into how we could use IOU-ring in Postgres, and that early research has sort of spun off a whole bunch of projects, and the work I'm talking about here has sort of come from that. Okay, so quick review of these functions. The basic read function in all Unix is you're pretty much just reading from a file descriptor, you're chucking data into a buffer, and you're saying how many bytes it is. And the P variant simply adds an offset. And that came about because in the 90s, when threading APIs were standardized, people quickly figured out that, well, you can't, if you've got one file descriptor and you've got two threads, if you want to do a random read and two threads are both trying to seek to a different position and read, that's not going to work. You'd have to have locking, or you'd have to have duplicated file descriptors, which is all a bit strange. So the P variants were invented. That's very simple. In Postgres, we're not using threads yet. Hopefully one day we will, and maybe that eventually will be a problem for us. But it was still convenient for us. And in fact, one of my first commits when I got started as a committer in Postgres was to change a lot of parts of Postgres to use pread instead of seek and read, because I was really annoyed by how often we call seek. And that's actually quite, we're not doing that because of anything to do with threading, but it did remove a bunch of complexity because we have these virtual file descriptors, so we had to keep doing all this bookkeeping and strange things. So one interesting thing with that was that to get that to work on Windows, we had to use a different function and sort of wrap it up and pretend that it had pread. Unfortunately, it has a slight side effect. It changes the current position even though it doesn't use the current position of the file handle. So we finished up deciding to access it as pgpwrite and pgpread everywhere in Postgres. So that's starting at the very simple end of I/O functions. So next, vectored I/O. What is it? You're reading from one contiguous chunk of a file and you're scattering that into many different buffers in memory. Pretty simple. So preadv is this, with IOV count of 1 is exactly the same as a plain old pread, but you can have an array of these vectors and scatter data into several parts of memory. And the opposite function is writing, of course, which is just the same. So who's interested in this stuff? Pretty much just databases. And the reason for that is that they have constraints on how they allocate memory. Probably most applications, if they want to read a large chunk of data from a file, they'll just make sure they allocate a big enough buffer to store that data contiguously, and they just don't have this problem. But because we have a buffer pool, we're trying to, the buffer replacement algorithm's job is difficult enough. We don't want to place extra constraints on where memory should be allocated. So, it works in these blocks. So in the end, it's quite good for databases to use vectored I/O. And that's the reason why you don't hear about it too much outside database programming. All right, so I had to change this slide on the plane when I was coming over here because I was going to say that that every Unix apart from one has the preadv and prwritev functions, but a little while ago I reached out to the Solaris kernel team and said, "Did you know your operating system is the last one on Earth that doesn't have preadv and prwritev?" And while I was coming over here with this slide deck, they replied and said, "Try now," and they just really, they just added those functions, so that was pretty funny. And then I replied saying, well, it's a shame that no one standardized it, and they sent a link to the proposal that they've now made to get POSIX to include preadv and prwritev, so that was pretty cool. Yeah, in the fullness of time, that should be whatever the next POSIX, assuming that goes well, they should become standard functions. But I mean, it doesn't matter, they're everywhere, and the only system that doesn't have them is Windows. And as far as I can tell, you can't actually implement synchronous preadv and prwritev or anything like that in Windows because it has scatter gather I/O, but it only has that for direct I/O, and which I'll talk about in a minute. And we need something a bit more general than that. So at the moment, when we just emulate preadv and prwritev with a loop just to get something going. All right, so the third thing is direct I/O. This sort of group of 3 features that go together in databases. Now, so direct I/O is a way, if you open a file and you tell the kernel, hey, don't do any buffering, try to minimize the buffering, and please let me read and write, access the disk as directly as possible. And again, it's mostly database people who are interested in this because the vast majority of applications like buffering and they don't want to think about this stuff. But because we have our own buffer pool in a database, it's not that great to have another buffer pool underneath us. And this, if you look at this chart that looks like it's been drawn with a crayon by a child, you can see that having double buffering sometimes has some quite interesting effects. And you can see that this is a PG bench run where if you set the shared buffers of Postgres to be big enough, then you get the high TPS number on the right. If you set it to be really low, you get almost as high, but somewhat strangely, in between those numbers, it gets worse as you increase it. And that's to do with whether, well, there's a couple of interesting things that jump out of this chart. One of them is that you can see that with buffered I/O, it's actually, the system is actually not that sensitive to how well you tune it if you set it pretty small, which is a pretty good default behavior. But if you want to use, like if you want to tune your buffer pool size carefully, and you turn it right up, then you can squeeze a bit more performance out of the system because you're not having to constantly move data between the two layers of cache. So yeah, just the kind of big idea is that dedicated high-performance database systems usually prefer to use direct I/O. Direct I/O is completely unstandardized, and there's this fantastic quote that comes from the ext4 README file, or I got this copy from their wiki. Yeah, it talks about how the exact meaning of ODirect has historically been negotiated in non-public discussions between powerful enterprise database companies and proprietary Unix systems, which I think is a pretty interesting quote. And at this conference, I actually, last year, I ran into someone who used to work for one of these proprietary Unix companies who told me a couple of anecdotes about that. And he had actually been embedded at a couple of different proprietary database companies for like 1 year or whatever. They gave him an office and they worked together, like kernel engineers and database people would work together and try and figure out exactly how to get the system to get the best performance. But somehow that stuff never made it into the, or any standard that's relevant to us. So it means that to get this thing to work in Postgres, we had to, we had to make a bunch of assumptions about what the requirements are, and there are a bunch of requirements. You have to, all of your buffers have to be aligned on memory pages, for example, and that's just something you have to kind of figure out. And so we came up with a bunch of rules that seem to work on every system that we have access to. Yeah. All right. So in Postgres 16, we added a setting. We called it debug IO direct because we don't really want anyone to turn it on yet, apart from for early testing, just to find out what file systems are going to break in strange ways or whatever. And because we don't have the rest of the asynchronous machinery yet to drive it really well, if you turn on direct IO in Postgres, you'll probably see a slowdown because the operating system won't be helping you with caching anymore. And that's the problem we need to work on next. So far, we've already managed to learn that Postgres interacts pretty badly with BTRFS when you turn direct IO on, for example. So that's been quite educational.
I would say that BTRFS is just broken.
Yeah. And specifically, that was BTRFS has checksums for every block. And sometimes when we're writing a block, during the write operation, another Postgres process can modify the page. So what should happen if you modify the data while you're writing it? Well, I don't know. You wouldn't expect the file system to blow up, though, would you? But that's what happens. So what happens is that it computes the checksum for that page or that block while it's writing it. And then if the data changes, next time you try and read that block back from the disk, you get an I/O error because the checksum fails. So that was a fun discovery. All right, so asynchronous I/O. This is the third thing. sorry, I said direct I/O is the third thing. Asynchronous I/O is the third thing. So the three things being vectored I/O, direct I/O, and asynchronous I/O. So who wants asynchronous I/O? Well, it's mostly the people who are doing direct I/O. I think in the networking world that's changing a bit now, but people who are interested in asynchronous access to disks, it's mainly database people. And the reason for this is that without the kernel helping you with buffering and read ahead and so forth, you need some way to get asynchronous I/O happening. And you need to drive it yourself. So the minimum way to do that kind of thing would be, like, without introducing any new operating system concepts, would just be to have extra threads and processes helping you running reads and writes in the background. And that is one of the approaches that you can take and that our prototype can do. But there are also a bunch of modern or even ancient operating system facilities to do that. Obviously going all the way back to the 60s, as I showed. All right, so I'm not going to be talking about I/O U-ring in this talk, but just like a super quick idea, sort of glimpse of what it is and where the ideas came from. It's basically that instead of having system calls where you enter the kernel and it returns control to you either asynchronous, either after sleeping or not or whatever. Instead of that, you've got these two queues. You've got a submission queue where you can put requests for it to do something into that submission queue, and it writes completion entries into this completion queue. And there's a single system call that you can use to tell it, hey, go and look in the submission queue, and hey, I'd like to wait for something to appear in the completion queue. And that's a kind of generalized replacement for, it started with just I/O functions, but it's turning into a complete interface to the kernel where you can do almost anything, replacing all of the system calls. So that gives you batching and it gives you asynchronous behavior. I think it's pretty cool. It's modeled pretty closely on the way that kernels and devices communicate. Even this terminology, submission queues and completion queues, that's the way that device drivers talk to actual disks. So there's a sort of a nice symmetry in the two layers of the system. So if you look at Postgres scanning a table in older versions of Postgres, you'll see that it reads 8 kilobytes at a time with p-read system calls. So you might see something like this in strace. And with the changes that have gone into v17, at least as far as beta 1, I mean, I can't promise it'll still be there when Postgres 17 is released, but fingers crossed. If you go and run a select count star on a table, you'll see a whole lot of p-read-v calls that are of size 128K. So it's doing a smaller number of system calls, transferring more data at a time, and not having to enter and exit the kernel so many times, which is just sort of a beginning. It's sort of a stepping stone towards more things. In future work and in prototype code that we have, the reads themselves, instead of being in standard sort of synchronous form in your backend process, could either be offloaded to worker processes and run ahead of time, so that you're counting tuples or whatever in a select count star statement. But there's helper processes that are running all these p-read system calls in the background. And that is kind of what you want for direct I/O, right? Because you don't want to have to wait. And in that way, your backend that's doing computation never goes off CPU. And that's the kind of ideal situation anyway. And in this I/O U-ring mode, there are no helper processes at all. Instead, it asks the kernel to coordinate the storage system doing that directly. So no extra threads or processes required. And that's kind of the sort of ultimate sort of ideal form of this, right? So you can see these sort of two layers where you've got a database up here which is driving I/O U-ring. It's telling the file system to please start reading a big chunk of data, and the kernel pushes that down into the storage layer, which involves another submission queue, which goes off to the storage hardware, and then in this way you get data transferred directly into the Postgres buffer pool without any copying being done by the CPU. So you kind of get data streamed into the buffer pool at exactly the right speed, so that the the query execution never has to wait for I/O. That's the kind of ideal form of where we're going here. And you can see this is Grommet here on a train, and representing the fact that it's getting data to be streamed in exactly in front of it, exactly at the right pace. Whether we can achieve exactly this level of perfection is another question. But all right, so that's the kind of very high-level background to operating system facilities. So read streams. This is the feature that we've got into Postgres 17. So reading blocks of relation data is an extremely common operation. All throughout the Postgres source tree, you'll see there are calls to this function read buffer, which takes a relation object and a block number, basically. And that function finds out if that block is already in the buffer pool, and if it is, it pins the buffer, meaning that it won't move, it stays put, and gives it straight back to you. So that function returns immediately if the buffer is already, the block is already in memory. Otherwise, it performs an I/O well, potentially it might have to kick some other data out of the buffer pool to make space, hopefully not, and commonly it performs a read system call to read the data into the buffer pool before pinning it and giving it back to you. That's an extremely common operation in the Postgres source tree, and you'll see that function being called all over the place in access methods for accessing indexes and tables and so forth. So the question is, if we want to change to something that can build larger I/O system calls and potentially push stuff into the background, we basically need to go and find all of the places that do that and apply some new magic and get them to coordinate grouping and ahead of time behavior. So a bad way to do that would be to try and get each part of the source tree to have to deal with those problems itself. Of course, we want to try and create some kind of reusable component to do that. And the reusable component we've come up with is a read stream. So if you look at a piece of code, this is actually more or less what PG prewarm looks like. It just has a loop over the number of blocks in a table. PG prewarm is an extension that is used to prewarm the buffer pool by loading a relation fully into the buffer pool. It's basically just a loop over read buffer. Normally, an access method would actually do something with the data in that buffer, but it just immediately releases it. So that's just looping over 0 up to n, calling read buffer, and then releasing those buffers, and that's a way that it gets data into the buffer pool. So the new version of that, which is in Postgres 17, instead of doing that, it creates a read stream and gives it a callback. And that callback is actually just something that counts from 0 up to n and returns those numbers. And then it loops over the stream, pulling buffers out of the stream, and then it releases the buffer immediately because this is just PG prewarm, which doesn't want to do anything with the data. So that code transformation is round about the simplest way to sort of see how to modify the code to use a stream. And that modification, that separation of concerns, separating the question of which block we need next from the consumption and use of those buffers, it allows the stream object to do whatever magic it feels like doing. So up here you can see this picture. You can see that at this end of this pipeline, you've got an arrow coming from the callback. It keeps calling that callback whenever it feels like it to try and build up a large combined I/O up to a limit of I/O combined limit. That's a new Postgres setting, which defaults to 128K, but you could change it. So it tries to build these groups of blocks, and each one of those then gets turned into a system call. Meanwhile, this loop down here where we say read stream next is pulling the individual buffers out. So behind the scenes, it can't tell, but behind the scenes, there are multiple buffers are being pinned at the same time, and the I/O combining is happening. But it doesn't have to think about that at all. So the end result of this, if you look at the old way, if you run strace, you'll see a whole lot of preread calls for 8 kilobytes, and if you look at the new code, you'll see a whole lot of prereadv calls for 128 kilobytes. So that was a simple sequential version. Here is what it might look like if you have random I/O. So imagine that In this case, the callback is maybe it's generating random block numbers for some reason. And the stream will detect that the I/O pattern is random, and it will not be able to do I/O combining because the block numbers won't always be next to each other. Maybe they will be sometimes, maybe they won't be. So it builds smaller I/Os, but when it sees that they're not sequential, it begins to issue what's called advice, telling the kernel, hey, I'm going to read this block soon. I'm going to read this range of bytes soon. And in that way, it's a kind of poor man's version of asynchronous I/O until we get to the next step in the project where we actually do the real asynchronous I/O in the background. So we're sort of going step by step here. And this is a trick Postgres has used for years to try and get some asynchronous I/O behavior. So we're continuing that trick for a little bit longer until we get to the real AIO support in later work. So yeah, so that's what, in that case, the setting effective I/O concurrency controls how many of these kind of imaginary I/Os are allowed to run at the same time. And on most operating systems, certainly Linux, that can give you an I/O depth that you can see with operating system tools. You can see that it's actually running concurrent I/Os in the background. So that later on, when it runs the read system call that is used to kind of complete that imaginary AIO, hopefully it doesn't have to go off CPU. All right, so how do we write these callbacks? So, I mean, the job of streamifying Postgres is finding all of the places where where it says read buffer and figuring out how to turn that into a stream and pull buffers out of a stream instead, but you have to give it the callback. So there's plenty of cases that are relatively simple. A sequential scan is relatively simple, and we have that working in Postgres 17. That's just a callback that generates literally sequential numbers, 0, 1, 2, 3, 4, for all the blocks in a table. The analyze code, so when you analyze a table, that's been streamified. So that's generating kind of random block numbers. I don't think I can say the algorithm is trivial, because I think it's Knuth's algorithm C for random block sampling or something like that. But anyway, that code already existed in a function. It just had to be put into the callback so that, yeah. So these are examples where the callback is relatively standalone, like it's not really interacting with anything else in a complicated way. So the transformation of the code is pretty simple. There are other cases where it's data-driven. Bitmap heap scan is a nice example. You know, that's something that used to do prefetching in Postgres using ad hoc code. Now it's been streamified, so that ad hoc code can be deleted. That's something that's work in progress. It's not part of Postgres 17, but it will be proposed for 18. And in that case, it's being driven by a bitmap, so we know what blocks we want. You just have to make a callback that can scan through that bitmap and spit out the block numbers. And recovery is another example. In crash recovery, we're running through the wall. We have to read ahead in the wall, find out what blocks are going to be accessed soon, and get a callback to spit out those blocks. We could imagine in the future perhaps trying to come up with something that can do heuristic look ahead in a callback. I don't know if that's going to turn out to be a good idea or not. Obviously, I mean, ideally, we would have precise prediction of the future at all times, but maybe that will turn out to be impossible. We'll see. So one of the complexities of this problem is deciding how far ahead to look. For example, we don't want to make it so that if you type select star from some table, limit 1, it immediately reads 128K or whatever large size. We have this ramp up idea where it starts off by just reading a single block. And if you consume that block, it'll then try and read 2 blocks. And if you consume those, it sort of builds its way up to the full size. And because we didn't want to make a system that generates a whole bunch of extra I/O that Postgres didn't previously have to do. We only want to make things better, not worse. So there's this concept of a look-ahead distance, and there's an algorithm to decide what it should be. So the distance actually changes over time depending on the observed behavior, how the stream seems to be behaving. It can tell the difference between sequential and random I/O. If the I/O is sequential, then there's no point in looking further ahead than the distance you need to build full I/O combined limit size I/Os. So I call that behavior B in the code. Behavior A is all the data is cached. We're scanning a table. It turns out that every single block that's in that table is in shared buffers already. There's no point in looking further ahead. So it just, because there's no I/O to be optimized. So yeah. And I call that behavior A. And then behavior C is when random I/O is detected. None of it is in the cache already. So we're going to be generating a whole lot of I/Os, and they're random. Now it's worth looking ahead quite far, because now we can use the effective I/O concurrency setting, which is Postgres' very bizarrely named setting to say how many I/Os you'd like to be able to do at the same time. And so this distance there's a sort of a heuristic algorithm to adjust it over time. And it seems to work pretty well, but I think over time we'll probably finish up tweaking it as we learn more. All right, so in the case of fully cached data, this whole scheme was designed to optimize I/O. But while working on it, it quickly became apparent that there are also opportunities to speed up even fully cached scans. For example, memory prefetching. So if your look-ahead distance is just 1, it's kind of interesting because now you know what page the scan is going to be looking at next, and you can tell the CPU about that, and that turns out in early experiments, and this is not something that's currently proposed, but in early experiments it turns out to be able to make scans like something like select count star from a big table that's fully cached already in memory, could be 10, 20%, or yeah, at least 10% faster through memory prefetching in simple experiments. So I think that's pretty interesting. And that was an unexpected discovery just while hacking on this stuff. But in the future, there are ideas around about changing the buffer mapping table in Postgres. And so another area to explore might be whether you can look up multiple. At the moment, there's a hash table lookup for every block that we want to look up in the buffer pool. If we had a tree structure, and if you know that you're going to be looking up these 8 contiguous blocks, then you could perhaps do that much more efficiently with one operation. All right. Another idea, at the moment, the way that streams work is that the block number callback spits out block numbers. Each time it's called, it spits out a block number. And that's the order that the buffers will come out of the other end of the stream when you're pulling buffers out. But actually, there are some workloads that don't care about the order of the buffers. Perhaps they're scanning all of the tuples on a if you're vacuuming a table, you don't really care what order you vacuum the blocks in exactly, necessarily. If that's true for a particular use case, then maybe we could have an out-of-order mode. Because if it turns out that some of the blocks are going to need some I/O, but some of them are in memory already, you might as well give those ones that are in memory already to the consumer. And early experiments with that show that you can get some speed up from that. There are actually a whole lot of other kinds of streaming I/O that we might want to look at for reads. Raw files in some places, or data a way to skip the buffer pool in some cases. Another thing which we haven't really looked into yet, but which could be really interesting, is whether we can use the same abstraction for dealing with sockets. There's a whole lot of ways you can speed up network I/O using the same style of programming. All right, so moving on to write streams. And most of the things I was talking about just then are actually in Postgres 17. The write part of this is something that I'm working on right now. So here I'm showing much more work in progress type stuff that might change completely. And the reason that we focused on reading first is that we wanted to come up with an interface that we could then. There's so many places in the Postgres source tree that read data. And so we thought if we could come up with a really good abstraction for that, there's ways for lots of people to get involved in working on different, we can sort of parallelize that work of getting all those read sites changed. But writing doesn't really happen in that many places. Pretty much, there's pretty much 4 or 5 places where data gets written out from the buffer pool in Postgres. Often it's the checkpointer. And it turned out to be really easy to get the checkpointer to drive a write stream. It has all the right conditions already. It already sorts buffers by block number before it writes anything out. So that was pretty easy to do. A much more complicated case, which I've been hacking on lately, and I've got some ideas about, and some working systems that seem to be kind of promising, is how you're supposed to deal with the cases when regular backends write data out, for example, during a copy or a create index or vacuum, for example. And so what we want to get to is a situation where, so traditionally Postgres, if you looked at a checkpoint or a copy or a create index, you would see a whole lot of P writes for 8 kilobytes. In early experimental code with synchronous write streams, it looks like this. Unsurprisingly, it's just done the write combining. There's also this sync file arrange thing, which I'll talk about in a minute. So the next steps are to get that offloading that stuff into the background, and finally into IOU ring. Vacuum is an interesting case because if you look at the system call trace for a vacuum, you'll see that it's doing both reading and writing. So it's going through a table, reading blocks in, vacuuming those pages, and some distance behind, it's writing them back out. It's also generating wall, describing the changes that it's making to those pages. In order to, with I/O combining, that unsurprisingly looks pretty much just the same. It's reads and writes that are interleaved in that way, but they're now larger. And the way that I've been trying to figure out, the way that I've been driving that is to reinvent, or basically it's another thing from Multics from 1965, which is called write behind. The idea being that, and we have this strategy thing in Postgres. It's been in Postgres for a long time, where whenever we're doing bulk operations like copies, we have this ring of buffers that we keep reusing, and that's to avoid trashing the whole buffer pool. If you're going to scan a whole table because you're vacuuming it, you don't want to get all of the data. You don't want to evict everything else from the entire buffer pool, so you want to constrain yourself to a smaller part of the buffer pool, and that's done using a ring. So one step is to teach vacuum to use a read stream to read pages in, and that happens in this ring. And then there's a write stream that runs along behind at exactly the right time, cleaning the pages that have cleaning the pages just in time so that it can reuse them, and in that way you finish up with combined IOs both in and out. I didn't explain that very well. It's actually quite complicated and quite hard to capture on a slide. So another thing that Postgres does, if you ever trace a Postgres backend, you'll see that it calls sync file range on Linux. And that's this flush after setting. So you have this backend flush after, checkpoint flush after, background writer flush after. And the reason it does that is because Linux is very lazy about writing data back when you're using buffered I/O. So if you write a whole bunch of data, it will just sit there in Linux's page cache until certain heuristics that it has are triggered to do with the amount of dirty data and various other settings in the kernel. So if we just wrote a whole lot of data out and we didn't do anything else until the checkpoint came along and called fsync, and we called fsync for each file sequentially, it would be extremely slow, and there would be no parallelism in the write back. So this flush after mechanism, actually traditional Unixes had this concept called write behind. And the kernel would detect if you were writing something sequentially and say, oh, this looks like a big write, a big sequential write. Probably the user is copying a file or something like that. So it would start immediately writing data back when it's detected that pattern. For some reason, Linux decided to not copy that behavior. I think an early version of Linux had it, and then they removed it. I don't know the history behind that. But anyway, Postgres essentially orders it to start writing stuff back some distance behind by calling sync file range. So if you look at a checkpoint or any other process that's doing a lot of writes in Postgres on a Linux system and trace it, you'll see that it's calling sync file range periodically after doing a whole bunch of writes. And that's another thing that can be folded into it's done in I wouldn't say it's an ad hoc way, but it's done there's a component in the buffer management code called write-back context, and we can kind of fold that into the write stream. And if you think about it, it's kind of the opposite of that advice we do when we're doing random reads. So, all right, so looking further ahead to where this is all going, so in V17, we've got the basic read stream mechanism. It's currently only being used by Analyze and sequential scans. Also PG Prewarm, which is kind of an educational toy, really. There are a whole bunch more read stream. Oh, the PG Prewarm is an extremely useful extension. You should check it out. But what I really meant to say is that the change to using a read stream was supposed to be educational, not PG Prewarm itself. So there's a whole lot of other potential uses for read streams, which will be proposed for 18. What I kind of hope to do by presenting this material is show people the idea and see if other people can see more places where things can be streamified, because ultimately to get best performance, we want to streamify everything, right? Hopefully we've come up with an abstraction that's easy enough to use that people can do that. So each access method, I was just talking to Jonathan Katz, who's really interested in PG vector. I'm sort of interested in finding out what kinds of, like, specific kinds of users that are doing large amounts of data I/O can we streamify next, and profitably. So at the moment, this whole thing is based on, yeah, Robert.
So I'm really curious, like, why would that not be every read buffer call in the back end?
It should be.
Okay, well, so we're done then? I mean, like, when you say, can you see more places that can be streamified? If the answer is that every read buffer call should be streamified, then, like, I guess.
Well, any read buffer call where there's a reasonably obvious way to predict them. So it's not literally every read buffer call. Read buffer should still exist. Yeah. Yeah. But I think in many cases there are ways to predict the future. Certainly anything that smells like a scan, you can probably predict the future. It can either be data-driven or arithmetic-driven. So at the moment, this is all synchronous I/O. Where this is really going is obviously asynchronous I/O. Probably in future versions, the current way that it works might turn out to be a mode that you can access with I/O method equals synchronous. But Andres here is working on true asynchronous I/O subsystem where you would have I/O method equals worker, which means background processes, or IOU ring, and potentially other things. The Windows native AIO, for example, would be another mode. And the concept here is that those changes can happen, and all of the code that is streamified won't notice. If you switch to the stream abstraction, then you get all the future magic improvements that happen below that. And that's the concept. And that's the end of my talk. All right, we've got some questions.
You're talking about the heuristics for the look ahead. I think the example was, select star limit 1, do 1 block, and then, see if you need to do it again, you do 2, et cetera. I'm wondering if there's going to be some sort of feedback mechanism there to gather metrics on how many unnecessary IOs I did, right, and some metadata around that so that we can further improve those heuristics in the future. Because I think the only way you're going to be able to do that successfully is to kind of get feedback from real life workloads, right?
That's true. So one thing is that there's probably a lot of work to do in statistics in general. At the moment, all of the statistics in Postgres kind of assume that IOs are 1 block. But actually now we have 2 separate ideas. We have block counters and IO counters, which are now different things because the IOs are different sizes, and we haven't really finished straightening all that out yet. But you're right that it would be interesting to have statistics about unnecessary extra IO. But that's already happening in the kernel level, right? Like the kernel does similar sorts of things. So yeah, a good question.
Yes. This I/O pipe system that you've invented seems to use a callback that exclusively returns block numbers. But is there also a plan or a system in place that would combine I/Os across multiple rel file nodes, for instance, or multiple forks?
Yes. So this is so at the moment we have only one kind of callback, but in patches that I have for recovery needs to do look ahead on potentially many relations. And I had to try and figure out whether, well, either you could have a hash table with loads of streams, but that's really hard and has other problems and kind of sucks, or you could have a multi-relation version. So there's a kind of extended callback where it gets to not just return block numbers, but also relations. Yeah, good question.
So I have a question. You've mentioned like the vast diversity of support for direct I/O on different operating systems. I was curious, do we know where the BSDs are in terms of direct I/O support, or is that something that was still?
Well, I can tell you. So it exists on FreeBSD. It exists for UFS. But probably most people are interested in ZFS, ZFS, however you want to say it. And OpenZFS is just in the process of implementing ODirect right now. There's a patch. It's been floating around for years. It hasn't been merged yet. Pretty close, I think. And that's so that should work. Yeah, the answer is yes, it works. But that stuff hasn't been released yet. So, and I haven't tested it myself. So. All right. Oh, one more question up here.
I think I've seen recently a bunch of posts about improvements to IO U-ring. And so I'm wondering, to the extent that we end up depending on that, how is that going to drive us to needing like super new kernels in order to get benefit from it?
The performance for buffered I/O gets better, I don't know, a year or so after it was AU-ring was introduced, which is by now a couple of years back, so it shouldn't overly restrict us. The performance improvements in AU-ring that were recently introduced are more for like complicated network I/O and stuff like that. So that's not, it would be nice in the future, but we're not there by a lot.
All right, everybody. Well, thank you very much, Thomas. Let's give him a big hand.